When we first learned the shortcut rules, we learned the power rule, if you'll recall, and the constant multiplier rule. But we didn't learn anything about the product or the quotient of derivatives. So let's go ahead and talk about the product rule first. So we're trying to figure out how to take a derivative of a product. So if we take the derivative of a product, the derivative with respect to x, of f of x times g of x, so I have two functions multiplied together. So the derivative, you might think, is just the derivative of each piece, but that's not true. What the derivative is the first function times the derivative of the second function plus the second function times the derivative of the first function. So the product of the derivatives is not the derivative of the product. That's kind of our important takeaway here. So this is our big note. The derivative of a product, f of x times g of x, is not equal to f of x, f prime of x times g prime of x. That means I can't just take the derivative of each piece and multiply them. So this is not true. Never do this. If you do this, you'll end up losing full credit because you are not getting the correct slope of a tangent line. If we want to find the derivative of a product, the derivative of the product is the product of the derivatives, is what this is saying, and that's not true. So let's go ahead and look at a quick example. Now, in our example, some of these we could do another approach, and some of them we can use the product rule on. Now remember, the goal is the same. I want to find the derivative of an expression, which gives me the slope of the tangent line at any point along the graph. So let's go ahead and look at the derivative with respect to x, and let's do x squared times, let's do the square root of x minus 4. So I have two functions here. So I have the function f of x, and then over here I have the function g of x. So you can see that I am taking the derivative of a product. Now, I could also distribute the x squared and then get rid of the fact that this is a product, but we want to run this one like the product rule. So the product rule states the first function, which is f of x is equal to x squared. So the first function times the derivative of the second function. So the derivative of, I'm going to get rid of this root. I want to focus more on the product rule, and adding the square root in makes it a little bit more complicated. So let's call this x, let's change that to x cubed. Okay, so the first function times the derivative of the second function, okay, plus the second function times the derivative of the first function. So the first times the derivative of the second plus the second times the derivative of the first. It doesn't matter which is first and second here. So if we decided to switch these around for some reason, it wouldn't matter. So again, we're trying to find that derivative. So this derivative is equal to x squared. And the derivative of x cubed minus 4, if you remember our power rule, you bring the 3 down, decrease the exponent by 1, and the derivative of a constant is 0. So first times the derivative of the second plus the second function, which is x cubed minus 4. Make sure you have these parentheses in place. And then the derivative of the second, the derivative of x squared, I'd bring the 2 down and then decrease the 2 minus 1 would give us 1. So here is my product rule. First times the derivative of the second function plus the second times the derivative of the first. And there's a lot of different ways to say that. This is the one I can remember. Now this would, if this was a 10-point problem, let's say on a assignment where you were showing your work, this would get you almost halfway. What we need to do is to make sure we can simplify from here. So again, this is the correct answer. Okay, but now we need to simplify. So we take x squared times 3x squared will give me 3x to the 4th plus, now here I'll need to take this 2x and distribute here and here. So I'll have plus 2x to the 4th minus 8x. Now it looks like I can combine some like terms here. So I'll have 3 plus 2 is 5x to the fourth minus 8x. So this is my derivative. We could call it y prime f prime of x. That's my derivative. This is the slope of the tangent line at any point along the curve. Now I want to do the same problem just another little way, so you can kind of be looking out for some shortcuts. I could have also taken the derivative with respect to x of x squared times x cubed minus 4, and I could have rewritten this before I even took the derivative. If we take x squared times x cubed, that would mean x to the fifth. X squared times a negative 4 is a negative 4x squared. Now when we take our derivative and I get my power rule, I bring the 5 down, so I have 5x to the fourth minus 4 times 2 is 8x to the first, the implied one. So you can see that these are equal, and I didn't have to use a product rule here. I just simplified first and then I applied just my good old power rule. Now that's not always going to work, but it's always good to kind of look at a problem and see if there's another way that you could rework it. Let's go ahead and look at an example of the power rule again. Now sometimes you could always expand any of these and avoid the power rule, but sometimes the numbers are so big and the powers are so large, it's more work to expand it. And we have to get into something called the chain rule before we can actually talk about taking like a binomial to a power. So for now, let's go ahead and just practice on some of these simpler power rules. So let's look at the derivative with respect to x, and let's do something, put up my brackets. Let's do 3x squared minus 2x times 4x cubed plus 1. So this is my first function, I'll call f of x. This is my second function that I'll call g of x. Now, just as our general rule down here, the derivative with respect to x, if I have a product, f of x times g of x, remember that's my first, times the derivative of the second. Now, a way we could write that, up above we wrote it d dx. We could also write it g prime of x. So the first times the derivative of the second, plus the second times the derivative of the first. That kind of looks like a 1. Let me make it look more like a prime mark. So this is another way you could write the power or the product rule. Either way, it doesn't matter. I'm going to include some steps in here, some work, so we can kind of see a little bit more of what's going on. So I'm going to say y prime equals. I don't want to say f prime of x equals because that's part of my problem here, so I don't want to get that confused. So I'm going to call this derivative y prime equals. Remember, our rule is the first function, so I just write that first function down, times the derivative of the second function. So I'm going to write the derivative of my second function. So I'm kind of laying out my plan here, plus the second function, which is 4x cubed plus 1, times the derivative of the first function. First times the derivative of the second plus the second times the derivative of the first. Now I actually have to do the work on this one, meaning I haven't taken the derivative yet. The only thing I've done is set it up. The derivative of 4x cubed plus 1, I bring the 3 down, but there's already a 4 there, so 3 times 4 is 12x. I decrease the 3 by 1 to a 2, and the derivative of a constant is 0. Okay, plus the first function times the derivative of the second function. So the 3 is already there. I bring the 2 down. 3 times 2 is 6. I decrease the exponent by 1. The 2 goes down to 1. Now over here, I have the derivative of a negative 2x is just a negative 2. Now why is that? That's because there's an implied 1 in my exponent, and when I bring the 1 down, negative 2 times 1 is negative 2, and that 1 decreases to a 0 in my exponent, and x to the 0 is 1. So being able to show all these steps is going to be very important because this is what you'll be graded on. And I would always really encourage you to write down the product rule before you start the problem, just to serve as kind of a quick reminder. Now this is getting us to our point where this is the correct product rule, but now I need to simplify it. Because when we use the product rule, a lot of times we like to take another derivative, a second derivative, and it's easier to take another derivative if I have this simplified. So I have 12x squared times 3x squared is 36x to the fourth minus 24x cubed. Now here, this was taking a monomial and distributing it through the binomial. But over here, I have a product of binomials. So I'm going to FOIL this or use the box method on it. It doesn't matter which one we choose. Now, because this is a plus sign, I don't need to have parentheses or brackets, but I'm going to put them up just so we can see that all the terms that follow are from this product. So I have 6 times 4 is 24 x to the fourth, so firsts. Then I'll go outsides minus 8x cubed plus 6x minus 2. So simplifying, I can drop those parentheses, and again, I really didn't even need them in there in the first place. I just wanted to have them in there so we could see where this product of binomials went to. And then my last step will be to combine like terms. Now it looks like to me my highest power is x to the fourth, so I'll have a 36x to the fourth and a 24x to the fourth. So 36 plus 24 looks like it'd be 60 x to the fourth. And then I'm going to go down a power. So negative 24x cubed, negative 8x cubed. It's going to be a negative 32x cubed. I don't have a squared. And then I have a plus 6x, doesn't combine with anything, and a minus 2. Okay, so there's my derivative. Now, this derivative is still the slope of the tangent line at any point along the curve that's defined. So I could use this to find the slope if I knew a value of x. So the application of these derivatives hasn't changed. It's just basically, how do I find the derivative of two functions multiplied together? How do I find the derivative of a product? So these have been a couple of examples of using that product rule. And remember, the big important thing to remember is that if I have a derivative of a product, it's not the product of the derivatives. Don't ever do that. Now the next one we want to look at is a quotient rule. We didn't look at this one before when we were looking at our power rule last section because it doesn't apply like the product rule is different than just taking the derivative of each piece and finding their product. I have a specific rule that takes place. So the quotient rule looks like if I'm going to take the derivative of a quotient, and we'll call it f of x over g of x, that derivative would be the bottom function times the derivative of the top minus the top function times the derivative of the bottom all over the bottom squared. Now there's a lot of different ways to say this. There's even like little rhyming songs and stuff I've seen on YouTube that you could look at. But this is kind of the way I remember it. Is bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now, this is only going to be true, of course, is if g of x does not equal 0. If g of x equals 0, this would be undefined, and I couldn't use the quotient rule here. Now, another way I've seen this written, this would be a high and this would be a low, so my low is my denominator, the high is my numerator. I've seen this written as low, like the word low, and then d high minus high d low all over low low or low squared. And I have a tough time remembering this one, so I have to run through it one more time to make sure I have it right. Low d high minus high d low all over low low. Now this d high is the derivative of the numerator basically. It's the derivative of the top. So it's not d times high, it's derivative of high. Remember our notation d sub x meant the derivative with respect to x. This means the derivative of the high, and this means the derivative of the low. So don't think you can divide through the low low and the d low over here. You'd have to go ahead and factor out before you could do that. So let's go ahead and look at some examples using the quotient rule. And I guess we better make a quick note like I did on the last one. And actually I should have put this in a different color, so let me do that first. I want the red to be a caution to make sure that you don't make any mistakes. So let's turn this to a different color. And we'll put the caution in red if it will let me. Okay, so our caution here, did we call it caution up top? We called it a note, so let's do the same thing here. I like the product and the quotient rule, they're kind of fun. So let's look at our note. The derivative with respect to x of f of x over g of x does not equal the derivative of the top over the derivative of the bottom. Never do this. And again, if you do this, this would be losing full credit on a problem. So be very careful about this. The derivative of the quotient is not the quotient of the derivatives. That only worked with the sum and the difference. The derivative of the sum is the sum of the derivatives. But it doesn't work like that for the product and quotient. That's why we need other rules. Now these product rules and quotient rules that we're looking at can be established using the limit definition of the derivative, but we're not going to focus on how they work. We're going to show how why they work and how we can apply them. So let's go ahead and look at a couple quotient rules. Let's look at the derivative with respect to x, and let's go ahead and look at a polynomial. Let's do 3x cubed minus 12x squared plus 2x plus 1. That's my numerator. And in my denominator, let's go ahead and try something like x squared minus 4. So for this problem, this is my f of x in the top, and this is my g of x in the bottom. Now if you want to do the high and the low, you can do that as well. But somehow you have to show your work and establish what's going on here. So I'm going to write the product rule, or sorry, the quotient rule in general to get started, to give us a reminder. And then we'll go ahead and apply everything to this formula. So again, I have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now if you wanted to use the notation that we used up above, the low d high and the high d low, you can. You can also write this using d dx of f of x if you'd like to as well. So let's go ahead and apply our formula to our problem above. So our problem above, it always starts with the bottom function. So I have the bottom times the derivative of the top. And I'm not going to take the derivative, I'm just going to write out what my path here is. I'm just going to write out the notation that says, and now I'm going to take the derivative. Okay, minus. Now the quotient rule has a minus sign. So minus the top times the derivative of the bottom. Now because there's a minus sign there, it's very important that we make sure this negative has parentheses following it. So the bottom times the derivative of the top minus the top. Hope we don't run out of space here. I think we are, so let's scoot this over. So bottom times the derivative of the top minus the top. Now we need the derivative of the bottom. And this is all over the bottom squared. Now it's not the derivative of the bottom, it's just the bottom function squared. So that was x squared minus 4 quantity squared. So we haven't found the derivative yet. The only thing we've done is kind of laid out the map. And this is a good thing to show because it establishes your work. And so that way if you have a mistake in here, I can see where it came from and give you lots of partial credit. But if you just start writing down functions, I'm not going to be sure where they came from. That kind of leaves it open for interpretation whether or not you knew how to use the quotient rule. But if you write out all these steps, I'll know you knew what you were doing, you just had a bit of an algebra error. So when I take the derivative of the green piece here, which is the top, the 3 comes down. 3 times 3 is 9x squared, minus the 2 comes down, 24x plus 2. Now the derivative of 2x is 2 because there's an implied 1 here, and the derivative of a constant is 0. Now again, I need to make sure I have this minus sign and I have a set of parentheses, and I distribute when I'm done simplifying. And the derivative of x squared minus 4 is 2x, and the derivative of minus 4 is a constant is 0. And this is all over x squared minus 4 quantity squared. Now, this x squared minus 4 looks like you might want to cancel these, but you don't, because you have to be able to cancel it out of the second term as well. So what we need to do here, this needs a lot of simplification, so your algebra skills really come into play. Gosh, I've almost used a whole page here. Probably end up using quite a bit more. So again, I'm still taking the derivatives. So what I'm going to do is I'm going to take this x squared and distribute it through here, and then I'll take the negative 4 and distribute it through here and write out my simplification. So it looks like I have 9x to the 4th minus 24x cubed plus 2x squared minus 36x squared plus, because I have a negative times a negative is a positive, 24 times 4 would be 96, x minus 8. Okay, so this is its expansion. It looks like we're already running out of room here. Hopefully we can sneak it in there. I'm going to leave the minus sign up, and then parentheses, and I'll take this 2x and I'll distribute it from there. So when I take the 2x and distribute, and remember the minus sign is right here, I'm not going to distribute it till I have the 2x done. I'll have a 6x to the 4th minus 24x cubed plus 4x squared plus 2x. And this, I close my parentheses and I drag along the denominator. Now I've noticed in a lot of your handwritten work, a lot of you drop steps, meaning you just drop the denominator until later on, but then you forget to put it back in. So one of the things I look for when I'm grading is whether you carry everything along to ensure that you don't drop anything. So here I have my 9x to the 4th, all of this. I'm just going to copy it down. I could combine some like terms, I guess. So 2x squared minus 36x squared would be a negative 34x squared plus 96x minus 8, and then I'll take the negative and distribute. So I have a negative 6x to the 4th plus 24x cubed minus 4x squared minus 2x. Now what I want to do up on the top is combine all the like terms I can. So I have 9x to the 4th minus 6x to the 4th. 9 minus 6 is 3x to the 4th. Okay, my next lowest power, I could probably look at the cube. So I have a negative 24x cubed, positive 24x cubed, and they cancel, so that I actually get 0 out of that. And then let's look at our squareds. Negative 34x squared. Let me change my color on that one. Negative 34x squared minus 4x squared would be a negative 38x squared. Okay, next let's see what we have here. I have a 96x and a minus 2x. 96 minus 2 is a plus 94. And then of course at the very end here I'm left with the minus 8. And that's all over x squared minus 4 quantity squared. Now there's no reason to expand the denominator. I want it to leave it in factored form. Now something might go on with the numerator. It doesn't look obvious that this factors. So this is my y prime. But if this would factor, I would want to actually factor it out and see if anything will cancel. So this is my derivative simplified completely. That one was a little bit ugly. Let's go ahead and look at another one. Let's look at the derivative with respect to x, and this is going to be 2x to the negative 3. I'm going to show you a couple of ways to do this same problem. And you'll see one way is really easy and you'll want to remember that way, and one way that's harder and you'll want to be able to see it that, oh, this is the harder way. Let's get back to the easier way. Well, this is just a good old power rule. So all I do with this one is I bring the 3 down and I decrease my exponent by 1. So 2 times negative 3 is negative 6. Negative 3 minus 1 is negative 4. Now, I can't leave it in this form because I never leave negative exponents. So this stays in the numerator. And this second one, because it has a negative exponent, this flips. So this ends up looking like a negative 6 on the top, x to the 4th on the bottom because it flips. So y prime would equal negative 6 over x to the 4th. Now I can also make this problem a lot more complicated. If I don't recognize that I can rewrite this, leaving the 2 up top and flipping this just looks like a quotient. So I do the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, so x cubed. Now the derivative of 2, that's the derivative of a constant, that's 0. So this would be x cubed times 0 minus 2 times the derivative of x cubed. I'd bring the 3 down, decrease the exponent by 1, so minus 3x squared. This is all over x to the 6th. So when I get done rewriting this, this whole first term is gone and I'm left with a negative 6x squared over x to the 6th. And of course this simplifies to a negative 6 over x to the 4th. The two of these x's cancel with 2 in the bottom, leaving me with 4. So here you can see I also get y prime equals negative 6 over x to the 4th. So we have the quotient rule, or we have the nice little power rule that we learned from the last section that I can also use with negative exponents. I think the power rule is a little easier here, so if you see something in this form, 2 over x cubed, something similar, flip that x cubed up top, make it a negative exponent, and I would use the power rule because I think it'll be a lot faster for you. Okay, let's go ahead and try a few problems. Some of these will be kind of a combined product quotient. Some will be using a bit of a power rule. Each one will have something a little bit different in them. So for our first example, let's go ahead and look at the derivative with respect to x. Let's go ahead and look at something like 3x squared minus 4 all over x to the 5th. Now if I wanted to, I could separate this into 2 different fractions and take the derivative of each one. But I'm going to go ahead and use the quotient rule on this one. So that would be the bottom times the derivative of the top minus the top, remember you need your parentheses here around that entire top, times the derivative of the bottom all over the bottom squared. So now we're ready to simplify this. So I'm going to call this y prime equals x to the 5th. The derivative of 3x squared is 6x. The derivative of a minus 4 is 0. The derivative of a constant is 0. Minus parenthesis 3x squared minus 4. The derivative of x to the 5th is 5x to the 4th. And this is all over x to the 10th. When you raise a power to a power, you multiply the powers. Or if you wanted to write this out as x to the 5th times x to the 5th and then write all the x's, you could see there would be 10 of them. So we want to continue to simplify here, so I have 6x to the 6th. Okay, so I have a couple different things going on here. I'm going to put up a minus sign, and then I'm going to take this 5x to the 4th and distribute. So I'd have a 5 times 3 is 15x to the 6th minus 20x to the 4th. So So we're getting close on this one. So let's keep simplifying. So I'm going to distribute the negative sign through, and I have 6x to the 6th minus 15x to the 6th plus 20x to the 4th. And remember, it's so important that you show all of your work, because that's kind of how you communicate what you're doing to me. You may be doing several steps in your head, but remember, you're trying to communicate what you're doing to me, so you need to slow that down and show those steps. Now this is a final answer, but it's not the final answer because I can simplify it further. Another thing while you're working that you shouldn't do, of course, is don't drop the denominator, don't drop any pieces of it, but also don't forget what you're trying to find. You're trying to find the derivative, so make sure you keep that derivative notation in mind. So simplifying, it looks like to me I can pull out an x to the 4th in the top. If I pull out an x to the 4th, I'm left with 6x squared minus 15x squared. Well, I guess I could have combined these first. Let's do that. I could have continued on with what I'm doing too. Either way it would have worked. 6 minus 15 is negative 9x to the 6th plus 20x to the 4th all over x to the 10th. So go ahead and factor out that x to the 4th, and I'm left with negative 9x squared plus 5. I'm sorry, that's not right. Plus 20. I was thinking I pulled out a 4. And this is all over x to the 10th. And of course, I have simplification that can occur here. X to the 4th goes into x to the 10th, leaving x to the 6th as the remaining factor. So this implies that y prime is equal to negative 9x squared plus 20 all over x to the 6th. So remember, don't drop your notation. Let's leave that y prime in there so we remember what we're doing. Some of these problems get pretty long, and by the time you get to the end, you can't remember what you were supposed to do when you got started, and that's finding a derivative. Okay, let's go ahead and look at another example. Let's look at y equal, let's do a combination here. Let's do 2x plus 1 times, oh geez, 2x cubed minus 3x to the negative 1 all over x squared plus 1. So you can see we have a lot going on here. In the numerator, I have a product rule. In the denominator, of course, because I have a denominator, I have a quotient rule in the entire fraction. There are so many different ways that we could start this problem. One way that we could do that is we could think about foiling this out, first outside, insides, lasts, and then just using a straightforward quotient rule. Another way that we could do this is just a quotient rule to get started. So that's what I'm going to do, is I'm going to do the quotient rule here. So let's go ahead and write out what that quotient rule is. I'm going to use my ddx notation. F of x over g of x. Now this is the deal here. This entire numerator is my f of x. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, so in our example, f of x is the top, and it's actually going to have to be rewritten as a product as well over g of x. So let's go ahead and get started on this one. So y prime. So that's going to be the bottom function, x squared plus 1, times the derivative of the top function. But the derivative of the top function is actually going to be a product. So the bottom times the derivative of the top minus the top, so that's minus all of this, times the derivative of the bottom. Now this is going to get pretty ugly, but remember, just stick to your basic rules, and remember, don't drop any parentheses. Don't drop anything else that kind of is indicative of important work. You know, don't drop the denominator, so let's go ahead and include that as well. That would be over x squared plus 1 quantity squared. Okay, so let's go ahead and have a look. Y prime equals x squared plus 1. Now, when I'm doing the derivative of this piece, I need to think about this as two functions. I have another, if we want to think about it, a of x times b of x. And so when I use the product rule here, I'll have the first function times the derivative of the second function plus the second function times the derivative of the first function. So this entire middle piece right here, bracketed in orange, is just the derivative setup for this piece. Okay, so I'm definitely running out of room here. So minus 2x plus 1 times 2x cubed minus 3x minus 1, and the derivative of x squared plus 1 is just 2x. And I said we needed to be careful, let's not drop that denominator, and that's all over x squared plus 1 quantity squared. Now you don't want to expand the x squared plus 1 quantity squared. Let's just leave that as is. So we still haven't really taken the derivative because I just have notation setups for a lot of this. So let's go to our next step, and again it might get a little bit worse before it looks any better. Here's that x squared plus 1. Now in parentheses here I have my 2x plus 1. Now the derivative of 2x cubed is going to be 6x squared. The derivative of negative 3x to the negative 1, I'd bring the negative 1 down. So I have a positive 3x to the negative 2. And if you need to pause and work that one through, remember you have to decrease your exponent by 1. And when you do that, negative 1 decreased by 1 becomes a negative 2. So I have plus 2x cubed minus 3x to the negative 1 times 2, because the derivative of 2x plus 1 is 2, because the derivative of a constant is 0. Go up, go my brackets, and then I'm on my second line here. Now with my second line, I think I could do a little bit of simplification, but I'm going to leave this one as is. I'm not going to try and expand and simplify this because it would get so awful. So let's leave this as. I'm going to pull this 2x out front over here just to make it a little bit easier to work with. And this is all over that denominator, x squared plus 1 quantity squared. So this is my derivative, this whole thing. This is the slope of the tangent line at any point along the curve. And remember, this is two lines. This is my numerator here to here, all over this denominator. So this whole thing is my derivative. Now, when I look at this, I think we probably could simplify this a bit, but in this particular form, it's pretty easy to see where all the pieces come from. So if something gets this intricate, I guess I wouldn't worry so much about simplification and just getting the derivative part right. Now let's think about what some applications are of our derivative. Remember, our derivative was the slope of the tangent line at any point along the graph, and our derivative talks about a change. And we talked about rates of change before when we were talking about f of t minus f of a all over t minus a, that type of thing. When we were looking at instantaneous rates of change, we take a limit or an average rate of change. Well, what we're going to be looking at here is we're going to be looking at growth rates. So for this example, let's go ahead and look at a quick setup. Remember, derivative means change. We're looking at rates of change. So for here we have the population of a culture of cells. And we'll say increases, so the cells are growing in the culture in the petri dish, and approaches a constant level. So this could mean something like there's only so much medium where they can grow in a petri dish, or there's only so much I guess food is one way you could say it, and then after that point they stop growing, the population stops growing. Now this constant level that they approach is called the steady state or carrying capacity. Okay, so that's its maximum value that it's getting to. So they usually give us some sort of a function that models that growth. So in this particular case, the population is modeled by the function. And so this function, let's go ahead and be pretty clear about it. P of t, and we'll define what these variables are, equals 400. And in parentheses I have t squared plus 1 over t squared plus 4. And I always put tails on my t so I don't get them confused with the pluses. So this is a t squared plus 1 over t squared plus 4. And of course this can only be true where t is greater than or equal to 0, because it's measured in hours. So time is in hours. So we can't have negative time. So this is my function, my p of t. Now for the first question here, let's go ahead and look at and approximately what time is the instantaneous growth rate the greatest. So that's one thing we could look at, and we could also look at a graph. So I think a graph might be interesting to start with here to give us an idea of what this looks like. So when we're graphing this, one of the things we want to make sure of is that we have the function entered correctly, and then we might need to be changing our scale. So to graph, let's go to y equal, and I see this huge number of 400, so I'm kind of keeping in mind that I might need to change my scale. Now instead of doing t squared plus 1, sometimes it's easier just to use our variable that's first, so that's x squared plus 1. We have to make sure we close parentheses, divided by open parenthesis, and then x squared plus 4. And then let's graph this and see what it looks like. I'm guessing we might not see much right now because of that value of 400. So I'm going to go to my window, and I think for my window, remember, time is positive. So this is meaning I have negative time right here. So I want to start my graph maybe at 0, and then let's maybe go out to maybe 10 seconds, or 10 hours, sorry, 10 hours. Now my y min, these are all positive numbers, so I think I can start at 0 here. And I have this value of 400 that keeps kind of coming up. So I kind of want to look at maybe 450 as my maximum y value. Yep, there's my graph. So the graph looks pretty good. This is my growth rate, and you can see it's starting to level out. And this value that it's leveling out at is called the carrying capacity, or the steady state that we just talked about. So let's go ahead and plop this into our lecture. And again, this is just a graph of that function. So as we're looking at this graph, these are a few things that I notice. On the horizontal axis, this is time in hours. So this is 1 hour, 2, 3, 4, etc. And you can see that this is approaching some value. And I'm not sure what this value is. I think it might come up with a horizontal asymptote here. That might be something that we can talk about in a little bit. So let's go ahead and graph this growth rate, and we have this. So this is the graph of p of t equals 400 t squared plus 1 over t squared plus 4. Now, just as a reminder, I can find a horizontal asymptote by taking the limit as t approaches positive or negative infinity. In fact, you should try both, but because these are both even powers, I just need to try the positive infinity of 400 t squared plus 400 all over t squared plus 4. So what I did is I distributed the 400. And the reason I did that is I wanted to take this limit using my shortcut rules. And if you notice, the numerator and the denominator have the same power. So that tells me my limit is the ratio of the leading coefficients. It's one of my shortcut rules from a previous section. So here we can see that this limit is equal to 400. Now I need to say y, because the degree in the numerator is the same as the degree in the denominator. So the limit is the ratio of the leading coefficients. So this tells me that y equal 400 is my horizontal asymptote. So I think what's happening here is this is starting to level out and go toward, it's not a very good straight line, level out and go toward this line of y equal 400. That's the carrying capacity or the steady state of this population. It's getting closer and closer and going toward 400 in the extremes, or the end behavior of the function. So that's my graph, that's my horizontal asymptote, and I used information from previous sections to come up with that horizontal asymptote, my shortcut rules. Let's go ahead and answer a question now. At approximately what time is the instantaneous growth rate? Remember, the instantaneous growth rate is given by this function. Actually, it's not given by that function. It can be found with this function. This is the population size, and if I want to find the growth rate, I could take the derivative. So approximately what time is the instantaneous growth rate the greatest? Okay, so that's the big question. Now another way to look at this same question is I could come up here to the growth curve and I could say, when is it steepest? Because that's what the growth rate is given by. It's definitely not steep up in here. It does look pretty steep down in here. In fact, right here it looks very steep. So I'm guessing maybe around 1 or 2 seconds is when that's occurring. But the way that we can figure that out is to take the derivative. So growth rate is given by cells per hour. Okay, so that means we need to take our derivative of our cell count. We need to figure out what p prime of t is from my original function. So in order to find p prime of t, I would take the, I'm going to move down a line here to give us a little bit more room. P of t is equal to 400 times t squared plus 1 over t squared plus 4. So p prime of t would be that growth rate, would be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, so this needs to be simplified. Now, we'll probably want to graph this growth rate eventually and then kind of compare it. So the derivative of 400t squared. So if I wanted to, I could think about this as 400t squared plus 400. The derivative of 400t squared would be 400 times 2 is 800t, and the derivative of 400 is 0. The derivative of a constant is 0. So here I have minus 400 times t squared plus 1. The derivative of t squared is 2t, and the derivative of 4, which is a constant, the derivative of constant is 0. And this is all over t squared plus 4 quantity squared. Now this is a really good example of why we want to simplify. I want to simplify this as much as possible in order to make it easier to work with. So let's go ahead and continue to simplify. I'll take the 800t and distribute it. So I think I'll have 800t cubed plus 3200t. Now here I need to take the negative 400 times t squared times 2t, which would be a negative 800 t to the third minus, so I'm going to have a minus 400 times 2t is a minus 800t. And again, this is all over t squared plus 4 quantity squared. So I think there's some things we can do here to simplify. Oh my goodness, they canceled out completely. So it looks like I have 800t cubed minus 800t cubed cancel. So I have p prime of t equals 3200 minus 800 is 2400t all over t squared plus 4 quantity squared. So this is not my answer, but this is my derivative. Okay, this is my rate of change. So this is the number of cells per hour. That's how it's changing. Now if I want to figure out where, again what my question was, is where at approximately what time is the instantaneous growth rate the fastest, we could plot this. That's one way we could find it. So let's use our same plot we have before, and let's include this 2400t on my next line. So we're going to keep our original. So 2400, and we're going to use x in place of t divided by open parenthesis x squared plus 4, and that's quantity squared. So this will be the red graph, and oh, it does show up. Okay, I thought maybe it might not. So I can see that it is maximizing right here. I want to know when it's the fastest. This is where the rate of change is the highest then. And it looks like it's happening between 1 and 2 like I thought, maybe closer to 1 though. So let's go ahead and graph this and snap it into our lecture. So being able to graph some of these is really important. So the original function is in blue, the derivative is in red, and this is giving me my instantaneous growth rate. So in blue we have our original p of t, and in red I have my derivative, the derivative of p, so p prime of t. So if I think about p prime of t, this is my growth rate. And in this particular case, it's my instantaneous growth rate. Now we don't know a lot of background yet about trying to figure out where this point is, trying to find this maximum value. I think it's right up here. I can estimate it. And it's also the steepest point on this blue curve. Now what we can do is grab our calculator, and we can find out what this maximum point is. And the way we do that is we come over here to Calc, and we go to maximum, because I want to find the maximum value. And I need it to jump curves, so I arrow down from my top to my bottom curve. See where this says left bound? That means I want to be to the left of this maximum point. So I can either arrow over, which is a very slow process indeed, or I can just put in a number like 0.5. And I can see that 0.5 is definitely to the left. And I can see that 2 is definitely to the right. I could arrow over if I wanted, but it's easier just to put in a number. And then it says, okay, go ahead and guess what you think it is. Well, I thought it was around 1. And then hit enter, and it found my maximum for me, 1.15. So I was close. I knew it was between 1 and 2 when I got started, and then I think it was kind of after I graphed it, I thought, you know what, it's a little bit closer to 1, which it definitely was. So when I look at this graph, it's providing quite a bit of information. So this point right here is the maximum instantaneous growth rate. So it occurs at time equals 1.15 hours, we'll say, and the rate at t equal 1.15 is 97.43 cells per hour. That's how fast it's growing at 1.15 hours. So we found a lot of information about this graph. It's pretty interesting to graph these and kind of get a feel for exactly what's being said and how easily it can answer the question. Now the last question we can answer about this is, what is the steady state population? We've actually already answered it. Now remember, another name for steady state was your carrying capacity. Now, we already answered this because basically it was our horizontal asymptote, and this was y equal 400. The horizontal asymptote of my growth, P of t, my population. So that was 400, and that was t squared plus 1 over t squared plus 4. So again, it was the horizontal asymptote of my population. Not any horizontal asymptotes of this, because we can see the horizontal asymptote of my growth rate function is 0. This is going towards 0, which means at some point it's going to stop growing because it's reached its maximum capacity. So that's just one of the cool things you can do with derivatives. So keep that in mind while you're working. Use your calculators to graph, but remember, on a test you won't have them, so you won't be expected to graph, but you could be expected to interpret graphs. So that's going to be a very important skill to have. As usual, if you have any questions, please let me know. You also have your Pearson Connect to a tutor. You can also take screenshots, send them to me via text, and I'm happy to answer right back. Good luck.